Myself, Assistant Professor Tukur Gupta from Ajay Kumar Garg Engineering College, Ghaziabad. The subject that I am covering in my lecture series is microprocessor. Subject code is KCS 403. Today I will be discussing microprocessor 8086 interrupts. What is interrupt? Interrupt is a method of creating a temporary halt during the program execution, and this allows peripheral devices to access the microprocessor. So when the normal program execution is going on, if some outside trigger comes and halts the program temporarily, then that is known as the interrupt. So there are various ways of triggering the ongoing program through interrupt. Like there can be hardware interrupt, there can be software interrupts. Similarly, some interrupts can be avoided and some cannot be avoided. So depending upon the type of interrupts, the interrupts have been broadly classified as hardware interrupts, software interrupts, and under the hardware interrupts, they can be categorized as maskable and non-maskable interrupts. So what is hardware interrupts? When the interrupt arrives to the processor through the hardware pins, then it is known as hardware interrupts. But when the interrupts are applied through programming, then they are known as the software interrupts. So if some instructions during the normal flow of the program, some instructions arrives which takes the flow of the control of the program to some interrupt location, to some vector location corresponding to the interrupts, then it is known as the software interrupts. But if the same interrupts arrives through the hardware pins, then it is known as the hardware interrupts. Then what is maskable and non-maskable interrupts? Sometimes the interrupts can be delayed or they can be avoided. Such interrupts are known as the maskable interrupts. But when the interrupts are of the utmost priority and they cannot be avoided or they cannot be delayed, and the ongoing current execution of the program has to be terminated and the interrupts have to be executed immediately, then such interrupts are categorized under non-maskable interrupts. The interrupts, those cannot be masked, or the interrupts, those cannot be avoided. The microprocessor responds to that interrupt with an ISR. What is this ISR? Interrupt service routine. The corresponding program which gets executed whenever some interrupt arrives. That is known as the interrupt service routine. And so it can be defined as a short program to instruct the microprocessor on how to handle the interrupt. Suppose on the arrival of certain type of interrupt, the microprocessor is guided to display a blue screen with certain message corresponding to that interrupt. So that is also the part of execution of that interrupt. So the microprocessor has been instructed to perform that function, to display that blue screen with certain message. So that is also interrupt service routine, that on the arrival of this interrupt, the microprocessor has to execute in this way. So that is known as the interrupt service routine. So as I have already told, that it is hardware interrupts are caused by any peripheral device by sending a signal through the specified pin. So when the hardware pin is involved in the execution of the interrupts, then it is known as the hardware interrupts. In 8086, we have only two hardware interrupt pins, that is NMI and INTR. So NMI is non-maskable interrupt. INTR is a maskable interrupt having lower priority. So NMI is having the higher priority as compared to INTR. And in return to these interrupts, there is one more pin, that is INTA, that is interrupt acknowledge. So whenever the interrupt arrives on the processor and the processor acknowledge it, so in return it sends a signal on INTA pin. So that is interrupt acknowledgement pin. What is NMI? It is a single non-maskable interrupt pin having higher priority than the maskable interrupt request pin, and this NMI is type 2 interrupt. So there are the interrupts in 8086 have been categorized under different types, and NMI has been categorized in the type 2 interrupt. So what are the various steps that which are executed as soon as the NMI arrives on the microprocessor have been discussed here. So when this interrupt is activated, these actions takes place. First of all, completes the current execution that is in progress. Then it pushes the flag register values onto the stack. So the flag register values are pushed onto the stack. Then next thing which is to be pushed onto the stack is code segment value. And next is the instruction pointer value of the return address of to the stack. Why these two things are loaded onto the stack? Because these two, code segment and instruction pointer, defines the effective final address. So these have to be pushed onto the stack. IP is then when the IP is existing IP value is loaded onto the stack. Now the IP is loaded with the new value, and the new value is the contents of the word location. This vector address is corresponding to NMI. So this has to be loaded into the IP, and the next address that is corresponding to CS, code segment register, and this has to be loaded, that is 000AH. Now the interrupt flag and trap flag are reset to 0. So these are certain steps which are executed whenever the interrupt NMI arrives on 8086 processor. Next important hardware interrupt is INTR. It's a maskable interrupt. First of all, it is maskable, and on the other hand, NMI was non-maskable. And this is maskable because microprocessor will be interrupted only if interrupts are enabled using set interrupt flag instruction. So whenever we want the microprocessor to execute the instructions, that is execute the interrupts coming through the INTR pin, then the interrupt enable pin has to be set. That is, the interrupt flag has to be activated. It should not be enabled using clear interrupt flag instruction. INTR interrupt is activated by an input-output port. If the interrupt is enabled and NMI is disabled, then microprocessor first completes the current execution and sends 0 on the INTA pin. So if interrupt is enabled, then INTR is accepted by the microprocessor, and as an answer to its acceptance, the microprocessor sends 0 twice on INTA pin. The first 0 means INTA informs the external device to get ready. That it informs the external device that I am ready to accept the data, and this is how the interrupt is executed. And during the second, the microprocessor receives the 8-bit data from the programmable interrupt controller. So this is how the interrupt coming from the INTR is executed. Next, this is a series of the steps whenever some hardware interrupts arrives on the 8086 microprocessor. So at the end of each machine, that is the instruction cycle, 8086 interrupts checks to see if there is any interrupt request. So if there is any interrupt request arrival on the 8086, then it responds to the interrupt by performing series of actions. So these are the series of actions. That is, whenever something is loaded onto the stack, what will happen first? That it decrements the stack pointer by 2. So it decrements the stack pointer by 2 and pushes the flag register on the stack. So first of all, flag register is pushed onto the stack. So this is how the main line program is going on. Now the interrupt service procedure arrives. What will happen? The flags are pushed. It disables the interrupt INTR interrupt input by clearing the interrupt flag in the flag. So now the interrupt flag in the flag register is disabled. It is cleared. Now it resets the trap flag in the flag register. Now again trap flag is cleared, which is lying inside the flag register. So these are the first 3 steps. Now again, what will happen? It will decrement the stack pointer by 2 and pushes the current code segment register contents onto the stack. Next, the CS, code segment register contents are pushed onto the stack, because these define the base address for the next that is the return address. It defines the base address of the return instruction. Now, it decrements the stack pointer by 2 again and pushes the current instruction pointer contents onto the stack. So, the next step is, first of all, the code segment was pushed and now the instruction pointer is pushed. These two, code segment contents, code segment register contents and instruction pointer contents, these define the 20-bit of physical address from where the execution has to be resumed. So, it does an indirect far jump at the start of the procedure by loading the CS and IP values from the start of interrupt service routine. Now, what has happened? It is a similar method that was executed in case of 8085. As soon as the interrupt arrives, the next instruction address will be pushed onto the stack, so that whenever the program control returns from the interrupt service routine, it comes back to the ongoing program. And it is possible only when the address of the next instruction, which has to be from where the program execution has to be resumed, they have to be saved somewhere. So, where they have been saved? They have been saved onto the stack. So, this is the similar method which was executed in 8086. So, here in case of 8085, the program counter contents were saved onto the stack. Here, the same role is played by code segment register and instruction pointer, because the code segment register and the instruction pointer stores the effective address, which is the address of the next instruction to be executed. So, as soon as the interrupt arrives, the contents of the code segment and the instruction pointer are saved onto the stack, and the code segment register and instruction pointer are loaded with the new values. And what are the new values? These are the starting address of the interrupt service routine. So, whenever during the execution of the interrupt service routine, whenever the return statement is executed, the control comes back to the address whose contents are stored in the stack. So, this is what is happening. So, an IRET, that is the interrupt return instruction at the end of the interrupt service routine procedure, returns the execution to the main program. So, this is how the hardware interrupts are executed, and this has been shown in this figure. So, first of all, the flags were pushed, interrupt flag and trap flag were cleared, then the code segment register contents were pushed onto the stack, then instruction pointer contents were pushed onto the stack, and then the ISR, that is the interrupt service routine address, is fetched. Now, here the registers, the contents are popped. So, instruction pointer, and whenever the iReturn instruction is executed, is encountered, then the instruction pointer and code segment register contents are popped from the stack, and lastly the flags are popped out of the stack. So, this is the whole procedure of interrupt execution. Now, we come to the software interrupts. Some instructions are inserted at the desired position into the program to create interrupts. So, these interrupt instructions can be used to test the working of various interrupt handlers. So, whenever the interrupts are provided to the main program through the programming, so then it is known as a software interrupts. It includes INT, that is the interrupt instruction with type number. So, this is the format of the software interrupts, INT and type number. So, it is a 2-byte instruction. First byte provides the opcode and the second byte provides the interrupt type number. There are 256 interrupt types under this group. Its execution includes the following steps: flag register values pushed onto the stack, code segment value of the return address, and IP value, that is the instruction pointer value of the return address, are pushed onto the stack. These are the similar steps which were happening in the case of hardware interrupts. Now, IP is loaded from the contents of the word location type number. that is the type number into 4. So this is how the address is calculated by looking at the type number. CS is loaded from the contents of the next word location. Now interrupt flag and trap flag are reset to 0. So this is a similar method of execution of the interrupts as was the case in hardware interrupts. Now the starting address of type 0 interrupt is 00000H for type 1 interrupt, and similarly it's 00004H, and for type 2 is 00008H, and so on. In this way, the interrupts types, the vector addresses corresponding to the interrupt types are calculated. So basically, the first 5 pointers are very important, and these are the dedicated pointers, that is type 0, type 1, type 2, type 3 and type 4. Type 0 is the division by 0 situation. So this generates an interrupt if such situation arrives. Type 1 interrupt represents a single step execution during the debugging of a program. So single step execution means that the single step, the execution, that is the debugging, is done during every instruction, and during every instruction, and the corresponding variable values or the errors are displayed during the execution of every single instruction. Type 2 interrupt represents non-maskable NMI interrupts. Type 3 interrupt represents breakpoint interrupts, and type 4 interrupt represents overflow interrupt. So whenever there is a situation of overflow, this interrupt arrives, this interrupt is executed. So among these interrupts, the two very important interrupts are breakpoint interrupt instruction and interrupt on overflow instruction. Let's discuss this. So INT3 is breakpoint interrupt instruction. It's a 1-byte instruction having opcode, that is CCH. These instructions are inserted into the program so that when the processor reaches there, it stops the normal execution of the program and follows the breakpoint procedure. So in this way, these interrupts are executed. So again, the same steps are followed during their execution. The flag register value is pushed onto the stack. The CS value of the return address and IP value of the return address are pushed onto the stack. Again, IP is loaded from the contents of the word location. Again, since INT3, this is the type number and this is multiplied by 4. This will give us some decimal value, and the corresponding hexadecimal value gives us the vector location. CS is loaded from the contents of the next word location. Interrupt flag and trap flag are reset to 0. So in this way, the this interrupt is executed. Now next important interrupt is INT0, interrupt on overflow instruction. It's again 1-byte instruction and their mnemonics is INT0. Opcode is CEH. As the name suggests, it's a conditional interrupt instruction. That is, it is active only when the overflow flag is set to 1 and branches to the interrupt handler. Interrupt handler is interrupt service routine, whose type number is 4. So if the overflow flag is reset, then the execution continues to the next instruction. Its execution includes the following steps. Again, the flag registers values are pushed onto the stack. Next, the CS and the IP values are pushed of the return address are pushed onto the stack. IP is loaded with the new interrupt service routine vector location, that is, it is interrupt 4, so that is the 4x4. Now CS is loaded from the contents of the next word location, and interrupt flag and trap flag are reset to 0. Finally, interrupt vector table, it's very important. It represents all the vector addresses of the interrupts available with the processor. So we see that 8086 gets the new values of CS and IP register from the 4 memory addresses. When it responds to an interrupt, the 8086 goes to memory locations to get the CS and IP values for the start of interrupt service routine. So for every interrupt service routine, for every interrupt, there is an interrupt service routine located at a definite address. So in an interrupt structure of 8086 system, the first 1 kilobyte of memory from 00000H to 003FFH is reserved for storing the starting address of the interrupt service routine. So this is the address range allotted to the interrupt service routines. So this block of memory is often called the vector table, interrupt vector table in 8086, or the interrupt pointer table. Since 4 bytes are required to store the CS and IP values for each interrupt service procedure, the table can hold the starting addresses for 256 interrupt service routines. So in this way, this table is having, so this is the table, this is the interrupt vector table, which is having the corresponding vector location for every type of interrupt. So suppose each interrupt type is given a number 0 to 255, and the address of each interrupt is obtained by multiplying the type by 4. Example, for type 11, interrupt address is 11 by 4, that is 44 in decimal, and the corresponding is 20002CH hexadecimal. Only first 5 types have explicit definitions such as divide by 0 and non-maskable interrupts, etc. The next 27 interrupts from 5 to 31 are reserved by Intel for use in future microprocessors. The upper 224 interrupt types from 32 to 255 are available for user for hardware and software interrupts. These are the user available interrupts. That's all for the interrupts of 8086. In next lecture, we will discuss the further topics related to 8086 microprocessor. Thank you.